This video is going to go through the parts of section 3.5, derivatives of trig functions, that we did not cover in class. It's going to prove one of the limits you see here, and it's also going to go through examples 2 and 3. So be sure to fill those in your notes. So what you'll notice here is this is obviously the sine graph, and we have this black tangent line here, right? And I've got the point A, which is the point of tangency, and I can actually grab that point and I can move it. So I can move it, say, over to there. And you'll notice that as I move it, the point B is moving. And this is what we've seen before, where basically B is has the same x value. If you look here to the left, A and B have the same x value. But B also has the y value, which is the slope of the line. So if I do slope of the line A, right, you can see the slope there is 0.61 over 1, and that's exactly what we have for our y value on B. And so as I continue to move my point, what do you notice? The slope is getting closer and closer to what? As our line goes to horizontal, the slope is getting closer and closer to?
Zero.
Zero. And so right there we have 0 slope, and notice where B is, B has a y value of 0. A and B always have the same x value. From there, I'm going to end up with negative slopes looking something like this. And they get super negative, and when I say super negative, I mean they get as negative as -1 right there. Right about there, we have a slope of -1. And then it's going to start becoming less negative as the line starts flattening towards a 0 slope again. And again, we continue on like this. What do you recognize the red curve is looking like?
A cosine graph?
Exactly, a cosine graph. And we know that if we're getting slopes of tangent lines as the y values of B, B is on the derivative of A. So we've noticed from the graph that the derivative with respect to x of sine x sure looks like cosine x. So there we have a kind of pictorial version of this thing. What we're going to do is we're actually going to prove it, but to prove it we need to have a couple of limits that we haven't seen before. And here are the limits that we haven't seen before. And so we're going to prove one of these limits using a picture and a theorem that you guys have already encountered. And then we'll just say the other limit is kind of done similarly. And then we'll prove the derivative. We'll see how it works. But anyway, we're going to prove that the limit as theta goes to 0 of sine theta over theta equals 1. We're going to prove that. That's what's coming up right now. So to do this, we're going to start off with a circle. There's the center of the circle, sort of. There's a radius. I'm going to have a tangent line coming up like that and like that. And so I'm going to label this A, B, C. This point here will be D. I'm going to draw this. We'll call that E. We're going to put a central angle here of theta. And we're going to say this is the unit circle, or a unit circle. So let's call this a circle with center A has radius 1. And angle theta is in radians. Now, I'm going to come up with 3 different areas. We have the area of the sector, and if you remember, a sector is basically a pie piece, right? Or a piece of pizza. And then we also have two triangles, which I'm going to do one in purple. This big one here, I'm going to do in purple. Okay, and this is a right triangle here. And then the other triangle I want to highlight, I guess I'll do it in green, is going to be this triangle here. And so we have three areas that we're talking about. We're talking about the green area, the gray area, and the purple area, okay? And so let's start thinking about each one of these individually. If we take the area of the sector, which is in gray, area of sector, you guys might remember this from a trig class or a pre-calculus class. I'm going to call it capital A sub sector, like that. And that equals to, you might not remember the formula, I don't know. You do know the area of a circle is pi r squared, right? And if we want part of the circle, we can take the angle theta and put it over all the way around, which is 2 pi. And so this is the fractional part of the whole circle times the area. That's basically what that is. And of course, that simplifies down to theta r squared over 2, because the pi's cancel. And because the radius is 1, this becomes just theta over 2. Okay? In other words, if theta is measured in radians, the area of that gray region there, is going to be the same as the angle in radians divided by 2. Okay, let's go ahead now and look at the green area of triangle ABD. Area of triangle ABD, that's equal to 1/2 the base times the height. Okay, now let's think about this for a second. The base, we're told that the radius of this thing from here to here is 1, or if you want to think about it from here to here is 1. So that's AB. But I want to come up with DE in terms of theta. So watch. If I take that triangle out, that right triangle that looks like this, theta 1 AED, this is a right angle, right? I want to figure out DE, right? So if we think about some trig, could we say that the sine of theta is equal to DE over 1, right? Opposite over hypotenuse. So that means that sine theta is equal to just plain DE. And so I can come back here in green and say that the area of this triangle is going to be 1/2 times AB is the radius 1 and DE is sine theta. In other words, we get sine theta over 2. And that's from looking at that small right triangle, right? This little right triangle, whoops, I did not want that color. This little right triangle in here in black. Okay, so let's look at purple now. We want to look at the area of triangle ABC. That's going to be something like this, which again is going to be 1/2 the base times the height, which in this case is BC. Okay, so now let's look at the purple triangle in a little more detail. The purple triangle, which is bigger, has a base of 1, right? This is A, B, C, and we want to figure out this height. So which trig function can we use now on theta to relate BC with theta and 1?
10.
Good. Tan theta is equal to BC over 1. In other words, tan theta is equal to BC. And so now I can come over here in purple. I've got 1/2 the base times the height, which is tan theta, and this becomes tan theta over 2. So what we have so far is we know that the area of the sector is 1/2 of theta. The area of the green triangle is sine theta over 2, and the area of the purple triangle is tangent theta over 2. Now, I want you to compare areas. Who's the biggest area? Just by looking at the picture, who has to have the biggest area?
Purple.
Purple. Excellent. So area of triangle ABC is the biggest. Who is the smallest area?
Sine theta over 2.
Okay, green, right? Area of triangle ABD. And then which area is kind of in the middle there?
The gray one.
Area of the sector. And we have that this one is biggest and that one is smallest. So there's our inequalities, okay? And they're going to be equal to each other, of course, when theta is 0. If you imagine theta going to 0, all the triangle's areas will go to 0. But anyway, let's go ahead and plug in what we know. We know that this one is tan theta over 2. Whoops. We know that this one is sine theta over 2. And the one in the middle is just plain theta over 2, like that. And here's what our goal is. Our goal is to get sine theta over theta in the middle. And so what we're going to do is we're going to multiply all 3 sides. Let me write this as a note so we have this. Multiply by 2 over sine theta. In other words, I'm going to multiply all 3 sides of this by 2 over sine theta. And so what we're going to get is tan theta over sine theta, because the 2's cancel. Theta over sine theta, because the 2's cancel. And just plain 1, because everything cancels. I think we can simplify tan theta over sine theta off to the side real quick. Just remember good old days of trig. Simplify this using identities. So that's sine theta over cosine theta over sine theta, which is going to give us sine theta over cosine theta times the reciprocal. And now we get these guys canceling. We're just left with 1 over cosine theta, right? So this becomes 1 over cosine theta greater than or equal to theta over sine theta greater than or equal to 1. Now we're going to take reciprocals and flip inequalities. And we're almost done with this thing. But just real quick, so we're clear, if I told you that 1/2 was bigger than 1/4, you would agree with that. But as soon as I took reciprocals, it's no longer true, right? So you've got to flip the inequality so it's still true, okay? So that's the same thing we're going to do here. We're going to take the reciprocals and then flip the inequalities. So this becomes cosine theta less than or equal to sine theta over theta less than or equal to 1. Now let's take limits on all 3 sides. And so let's see if we can do direct substitution. Can we do direct substitution on this limit here?
Yes.
Yeah, what do we get?
1.
So that's 1 is less than or equal to. Let's leave this one alone for a moment because this is actually the thing we're looking for. And of course, the limit back here, the limit as theta goes to 0 of 1 is just plain 1. So what do you think we can say about the limit in the middle?
It's also equal to 1.
Okay, how do you know that? Which theorem?
I forgot the name.
Squeeze theorem?
By the
Squeeze theorem.
squeeze, yeah, that's
Yeah,
good.
squeeze theorem.
By
Yeah.
squeeze theorem, the limit as theta approaches 0 of sine theta over theta is equal to 1. So we just proved that first, what they're referring to as an important limit in the notes. Okay, and the reason these are two important limits is because we need them to prove that the derivative of sine is cosine, which is what we're about to do on the next page. The other limit, cosine theta minus 1 over theta equals 0, is done in a similar way. But let's go ahead and just leave it with just saying we've done one of them. That's good enough. So on the next page, you have your next set of 6 derivative formulas. Okay, so at some point we'll put them all together in one place, and we'll see them all together, and these need to be added to the list that need to be memorized, right, along with the ones that we've already seen. But let's quickly prove now a couple of these. I'm not going to prove them all because, as you'll see, some of the proofs end up being the exact same with just different trig functions involved. But let's go ahead and first prove that the derivative with respect to x of sine x is equal to cosine x. That's what we're going to prove right now. So here we go. Derivative with respect to x of sine x, using our limit definition, the limit as h approaches 0 of sine of x plus h minus sine of x all over h. And for those of you who might remember a little bit of trig, you had a formula for sine of a sum. And I'm going to go out on a limb and say most of us have forgotten it. So I'm going to just remind you how it goes. But does anybody remember it? Does anybody want to throw it out there? Or should I just write it?
Isn't it cosine x sine x plus or maybe it's the opposite way.
How about that? Sine x cosine h?
Yeah. Sine x cosine h. Yeah, and then the plus. Okay.
Yeah?
Yep.
It's been a while, but that's what we have going on here. Minus sine x all over h. So that's just a sum formula back from trig. And what I'm going to do now is I'm going to break this up into a couple of limits. I'm going to take this and this together. Okay, here I'll do it in green over here. So I'm going to have the limit as h approaches 0. I'm going to take sine x cosine h minus sine x over h. And then to that, I'm going to add the limit as h approaches 0 of cosine x sine h over h. Okay, so what I did here is I split these up in a very specific way, and you'll see why I split them up this way in a moment. The first one in green, I can factor out a sine x in the numerator, and because that sine x doesn't have any h's involved, I can take it out of the limit. So I end up with cosine h minus 1 over h, like that. So we have this limit, plus I can do the same thing. I can factor out a cosine x, and then I have the limit as h approaches 0 of sine h over h. Okay, so here, let me actually do it this way instead. Okay. Now, if you look at what's in the parentheses there and kind of scroll back to the page above, this limit in gray here on the previous page is 0 right there, right? It's just instead of theta, we have h. And the other limit is the one we just proved. So we end up with sine x times 0 plus cosine x times 1, which will give us cosine x. And we've just shown that the derivative of sine is cosine. Now, in practice, what you're going to do is you're just going to remember, oh, the derivative of sine is cosine, so therefore I can just use that and move on. Let's go ahead and prove just 2 more of these, and then we'll say the others are the same. So I want somebody out there to choose. Do you want me to prove cosecant or secant? I will say that I believe the proof for secant is in the book, but I'll do either one. Which one do you want to see? Secant or cosecant?
Cosecant.
Cosecant. Okay. So if we're going to prove the derivative with respect to x of cosecant is equal to all that garbage, well, let's start off by, again, using some trig that we know. This is the same as 1 over sine x, right? And so if I have that, I think I can use the quotient rule on that. Hopefully you guys have been practicing with your quotient rule, but the derivative here is going to be the bottom function times the derivative of the top minus the top, that's a 1 there, times the derivative of the bottom all over the bottom squared. Okay, so we have the bottom times the derivative of the top minus the top times the derivative of the bottom. And that's going to be, well, the derivative of 1 is 0, right? The derivative of sine is cosine. And on the bottom, we have sine squared x. So this becomes negative cosine x over sine squared x, which can be rewritten as negative 1 over sine x times cosine x over sine x, which gives us negative cosecant x cotangent x. And that is the derivative of cosecant. Okay, so we've done that one. So far we've proved this one and this one. The proof for cosine is kind of similar to the proof for sine. The main thing we have to notice is notice the negative on that, right? The negative on the sine, okay? So be aware of that. And then the derivative of, say, tangent or cotangent, they're very similar. I'll do cotangent because I think the other one's in the book. That is a matter of using the quotient rule again. Because cotangent, you know, is cosine x over sine x. So when we apply the quotient rule, we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, which the derivative of cosine is negative sine, and the derivative of sine is cosine. So we have negative sine squared x minus cosine squared x all over sine squared x. But what do you recognize about that numerator?
It's equal to negative 1.
That's right. If you factor out the negative, you've got the sine squared x plus cosine squared x, which is your Pythagorean identity, like this. So you get -1 over sine squared x, which is negative cosecant squared x.
So that was the proof of the derivative of cotangent equaling negative cosecant squared. And now we'll go on to examples 2 and 3.
An object hangs on a spring, making it 2 meters long at its equilibrium position. I'll draw this in a moment. If the object is pulled down 1 meter and released, it will oscillate up and down. The length L of the spring after t seconds is modeled by the function L of t is equal to 2 plus cosine of t. And so part A is pretty straightforward for us. They want us to find the velocity. And all we have to do to find velocity is, the velocity function is to take the derivative of the position function. And the derivative of 2 is 0. The derivative of cosine is negative sine t. So even without a picture, that part is pretty straightforward. And I will get to the picture in a moment. The next one, what position is the speed of the object maximized? Well, let's think about what that means. Speed is equal to the absolute value of velocity. That's what speed is. Remember, velocity has direction from the origin included in it as a positive or a negative, but the speed is simply the absolute value of that. So in this case, we get negative sine t in absolute values, which obviously is the same as just plain sine t like that. And that's going to be is maximum. Well, you know that the greatest value of sine is 1 when sine t is equal to 1. And that happens cosine t is equal to 0, right? Sine t is 1, right? Sine t is its maximum right there at the same value when cosine is 0. So if we look above at L of t, so speed is maximum when L of t is equal to 2 plus cosine t being 0, it's going to happen at 2. Okay, let's do one more. Let's go ahead and find the acceleration of this object. And then, I don't know, I want to try, well, I do know why. I want to try doing the picture of this last, because in the past, the picture, I don't think helped answer these questions very well. So I want to see how much of this we can do without the picture. To find the acceleration, that's just the rate of change in the velocity, as we've discussed before. And the derivative of, that's going to be the derivative with respect to t of negative sine t. The derivative of sine is cosine, so we have the negative in front. There is our acceleration. And they want to know at what position the acceleration is 0. Well, acceleration, which is negative cosine t, is equal to 0, happens when the cosine of t is equal to 0. And the position L of t, which is 2 plus cosine t, we put a 0 there and we just get 2. Now, we've answered everything, but let's kind of get a sense of what it is that's going on here. If I've got an object hanging from a spring so that 1, 2, 3, these are distances from here, which is obviously 0. And at equilibrium, it hangs at 2 meters. So this object which I'm just going to make it, I don't know, something like that. There's my object. And it's on the spring. So that at equilibrium, it's right there. And what they're saying is if I come along and I pull this thing down to here and let go, that object is going to go up and down like this, right? It's not moving to the right at all. It just keeps going up and down like that, okay? And the distance, L of t, is the length of the spring after t seconds. So L of t is whatever that is, that distance at any given time t. And so at its shortest, it's going to be 1, right? Because it's going to be 1 at its shortest, right? Where it's all compressed, the spring is all compressed. And at its longest, it's going to be 3. Okay, not the greatest drawing, but hopefully that kind of gets the idea across. And it just keeps going back and forth, back and forth. And so what we end up with is the length goes from 2 to 3 to 1. And because it's something as simple as 2 plus cosine t, you guys have graphed that sort of thing, right? This function here, this function in yellow, you've graphed it in trigonometry and in pre-calc. It's just the cosine graph that's been shifted up 2 units. So as time marches along all the way out to 2 pi, maybe here is pi, there's pi over 2, here's 3 pi over 2. If we pull this thing down to 3, it starts off at a length of 3. And then when we let go, it shortens to a length of 2, and then to a length of 1. And then it comes back down to a length of 2, to a length of 3. This is the graph. Not very well drawn, I know, but that's good enough. L of t is equal to 2 plus cosine t. And we see that the speed is going fastest when the length is 2. When we let go of it, right? When we let go of it right here, it speeds up into that equilibrium height, and then it starts slowing down until it gets to its highest point and stops, and then it comes back down and speeds up, and then slows down until it gets to there, and so on and so forth. So the speed is maximum at 2. That's the fastest it's going to go before it starts getting slowed down, either by the by gravity or by the resistance of the spring. That's the idea with that one. It's a little funky, but hopefully that kind of made sense. Does anybody want to ask about it before we look at the last example for this section?
Yeah, how did you get the velocity of the object?
So the velocity is always going to be the derivative, the rate of change in the position function. Remember we did it with s of t, and we saw that v of t was equal to the derivative of s of t. Remember that from 2.7 or 2.8?
Yeah.
So this tells me, the s of t tells me the position at any given time t. If I want a rate of change in position, that's going to be a change in position with respect to time. That's going to be the first derivative. And the second derivative is the rate of change in velocity, which is the second derivative of position. That's the acceleration. Cool?
Okay.
Yeah, this is worth remembering. We're going to be dealing with this a decent amount here. All right, so we only have 2 little examples here, but both of them are going to use the limits that we talked about, the new limits in this section, right? One of them being, let me remind you, the limit as theta goes to 0 of sine theta over theta. We proved that one using the circle and the triangles and the sector. And then the other one that we saw was that the limit as theta goes to 0 of cosine theta minus 1 over theta is equal to 0. And so we're going to try to find these limits in these problems. So for example, with this first one, we have the limit as x approaches 0. You guys know that you can rewrite tangent as sine x over cosine x, and all that is over x. And we can rewrite that if we imagine multiplying top and bottom by cosine x, we get 2 sine x over x cosine x. Okay, all I did there was I multiplied here by cosine x and here by cosine x. And of course, those will cancel. And so now I'm going to split it up into two limits. Whoops, limit as x approaches 0. This is going to be the limit as x approaches 0. I'm going to split it up this way. And the reason I split it up that way is because this limit in yellow, we know what that is, right? It's over there. So we know that's 1. And this other limit, we can do direct substitution because we can say 2 over the cosine of 0. We know that the cosine of 0 is 1. So this is really 2 times 1, or just plain 2. So these limits are limit problems that we couldn't do before because we didn't have these two special limits that we can substitute in. All right.
Sir?
Yes, please.
How did cosine x turn into cosine times 0?
Well, it's cosine of 0, right?
Uh-huh.
All I'm doing is from here to here is direct sub,
Okay. All right.
right? And the cosine of 0 is 1. So good?
Yeah, thank you.
Sure. Okay. Let's look at the next one. Now, again, I want to probably create this one here. And if the bottom were 3x, if this were 3x, I'd be in pretty good shape, right? Because then the angle above and the angle on the bottom would be the same, right? I'd have my thetas, right? I'm talking about this theta in pink here and this theta in pink here would be the same if they were both 3x, okay? So let's notice that I can rewrite this like this. Okay, what the heck did I just do so far?
Pulled out a 1/5.
I just pulled out a constant factor of 1/5, right? Now, what do I really want to see in the bottom there? I want to see 3x. Okay, so I'm about to write something. I'm going to do it in green so it stands out. And I want you to tell me why this is allowed or why it's not allowed. Okay, so I'm gonna put in green here a 3 down here and a 3 up there. Is that allowed?
Yes.
Why?
Because when you
Because
distribute, it simplifies.
Okay,
Yeah.
so when you cancel the 3's down, it takes you back to where you were?
Mm-hmm.
Totally good. Does anybody else want to ask about that? The 3's cancel. I'm kind of skipping a step. I could forget this for a minute. What if we were to write it this way? Put the 3 up here the 5 down there times limit as x approaches 0, right? The 3's definitely cancel, and then everything multiplies back to this. And if we now take out the 3/5, we now have a limit of sine 3x over 3x. Now, if, or I'll just say let theta equal 3x, so as x goes to 0, theta also goes to 0, right? If x went to 0, meaning x is getting super, super small, either positive or negative, even if you multiply it by 3, you're still getting close to 0, right? So theta goes to 0. So this becomes, this is the same as 3/5 the limit as theta goes to 0 of sine theta over theta, because I replaced 3x with theta, right? And now we have the yellow limit over there, and we'll have 3/5 times 1, which is equal to 3/5.